If you ever find yourself in Seattle near the end of Boeing Field's runway, now known as King County Airport, there is a nondescript building that is well worth a visit. But you really ought to know where to find it, because there are no windows in the building and the door is hidden at the back. Yes, you guessed it, it's a telco exchange building that houses a hidden gem, the Connections Museum. You can tell this is the empire of telephone. There's no doorbell, but there's a phone. Hi Peter!
Hi. Welcome!
Mark.
Telephones everywhere.
Whoa! So this used to be an actual interchange, right?
Still is.
Still is.
An actual telephone company central office building.
Oh, I recognize Crossbars. This guy I know. Oh, I recognize a ringing machine. Because
Yes.
I've watched your video.
Because
so.
you've watched
Sarah's video
about ringing machines.
Yes, they have a YouTube channel linked in the doodly-doo, whose host Sarah is the one that invited me for the visit. She'll join us later, and yep, that's where you can learn everything about ringing machines and anything else in the museum. And well, I saw a ringing machine with the small little box, and this is this humongous thing from the 1930s, right?
Right, but they came in different sizes depending on the size of the central office and the number of subscribers. So there's a smaller one there.
Oh, that's an itsy-bitsy one.
And
This is my hand for comparison. Yeah, so they had this predates electronics, so they had no amplifiers, so they had to get the strong signal from the motor straight, right?
Yes.
And it's fairly high voltage too. All the wiring at the back, relays galore.
So 1938 design, 1948.
38 on the left over here.
That is the test desk, as they called it in their terminology. Right? The blinking lights. This is the blinking lights.
But this stuff lives hidden. This has been my whole career. I'm a telecom guy, right? But no, fiber one. And I can never explain to people what I do because you never see that stuff. But it's immense amount of technology. That's how all meters should be.
So this is the power panel. Originally also from 1923. Everything, of course, runs on 48 volts DC.
Ah yeah, so you can back it up with batteries.
So you can back it up with batteries. Do you know what this is?
It's a fuse.
It's a fuse, yes. Do you see what the rating on that fuse is?
It's 4800 amps.
4800 amps, yes.
I know, because you have all those magnetics to power.
Right.
And then rows and rows of stuff. Oh, it's live. Blinking lights.
This is the television broadcast transmission test and monitoring. Some more teletypes.
Yeah, you can never have enough teletypes. Oh, reperforator. Model 15. Oh, 19. Right there. And a... What is that? It's a 28?
This is a 28, yep.
Yeah. And a 35 when you have one of each. So this place is overwhelming. There are several floors of this stuff, all working. I'll try to give you an organized tour, starting with the beginning of the telephone exchange up to the Bell Labs early computerized stuff, which maybe will whet your appetite to go see it for yourself. So we'll start with the beginning here, with a crank telephone. What does a crank do?
So this is how you get the operator's attention that you want to make a call.
And it operates a little electricity generator called a magneto that gives 100 volts, so quite a bit, to the switch over there. Go for it, Colin. There you go. So the 100 volts went over there and alerted the operator we wanted to make a call. So now Pete is going to be our operator. Go for it, Colin.
So I see that 65 wants to make a call. I take my cord and plug it in at 65.
So that has the incoming. Oh no! 65 is going to be the jack where it's coming in. Then it goes into the machine.
Jack. Right. So now it comes in here, and now I can speak to my subscriber and say, "Number, please."
Number 14.
Connecting you now, sir. So now I take the front cord. These cords are in pairs.
And you can take
and
any
I
cord.
Plug it in at 14.
Okay.
And now I have my own crank and magneto to ring the wanted subscriber, and I have to pull this switch towards me while I'm doing that.
And there's the phone right behind you. Okay.
And now 14 rings.
Okay.
And if I then pick up. Hello, Colin. How are you?
Hello.
All right. So you have a phone, and it's basically a two-wire connection that goes through the machine straight. 2 wires to 2 wires.
2 wires to 2 wires. Yep.
The circuit is powered by the calling telephone, right? So Colin, you have something in here. You have the batteries. So everybody has to get their batteries ready or it's not going to work.
They have to send somebody around with a wagon every 6 months to replace all the batteries in everybody's telephones.
Therefore, the first big step for central office is central power.
Right, what they called common battery.
Right. And that's when they switch from relatively low voltage to 48
That
volts.
is when they switch to the higher voltage, yes.
And actually, these two explain the difference. This one is a local battery, and this one's the next evolution. It's a common battery.
Common battery board, yep.
And you were telling me that one of the other advantages is common battery, that it had power, therefore they could go away from the little flap.
Instead of the little flaps dropping down, they could have indicator lamps, and the jack is conveniently located right below each lamp, so it makes it quicker for the operator to see which jack they need to plug the cord into.
That's progress. And Colin, what is this bigger one?
So this is a toll board. So this is for handling not local customers, but handling their long distance calls to distant cities. All the jacks here, instead of going to individual customers, they go to this city, that city, this city. And so this is how the operator would connect you to the operator in that distant city to connect your long distance call.
Local was, we'll see it in a second, was automated first.
Right, the earliest dial systems only handled calls inside of your city.
Right. And toll, that's synonymous for, well, now you have to pay more.
Right.
When you do long distance, and that is a bigger and more difficult problem.
Right.
And it stayed manual for a long, long time.
Right, they didn't implement customer dialed long distance until the 60s, and so up until then, even if you could dial your neighbors, you still could not dial to a distant city. So you would either ask the operator or dial for the long distance operator. They would have a headset to talk to you,
right,
and ask what number you wanted to call.
Right.
And then they would ask the route operator how to make that call, so that's another operator involved. And then they would connect you to whatever the next city was in the path to getting to the city you wanted to talk to.
I had not realized that the long distance switching stayed manual for so long.
Right, it's a more complicated problem.
Now, Peter, you are going to show us the next step of evolution where local switching is done automatically thanks to this.
So instead of having to speak to an operator, you could dial the calls yourself, starting in about 1898.
Oh, that early. And that just creates pulses, right? One pulse for one, two pulses for two.
One pulse for one, 2 pulses for 2, on up to 10 pulses for 0.
All right. And then you got to decode this thanks to this thing over here. Well, I have to take a step back. This is huge.
Yes, this is the thing that an undertaker from Kansas City by the name of Almond Strowger invented in 1892. Each pulse that comes in from the telephone activates this A relay one time, and each of those pulses then causes the solenoid to step the wiper up one
Get counted,
level.
and then there's
Counts.
the contacts are made down on this wafer thingy,
Yes.
and that also can rotate.
Okay, here it goes up. And then around.
Alright, so that's 2 degrees of freedom. Here you go.
Hello?
So this whole bank of things can handle right now about 200?
About 200 subscribers.
So it's this.
So all of those subscribers, this big bundle has those subscribers' phone lines connected into the first, into the line finders.
These are all the phone lines that the switch supports. It's just amazing wiring. So that's pretty impressive, but you tell me it has limitations.
The problem with this system is that it does not scale linearly. As you get to have 100,000 customers, you need so much of this equipment that it's just not economically feasible anymore. And so they needed a solution to that problem.
Okay, let's go see it. Alright.
And now we come to the way Western Electric solved that scalability problem in 1923.
And what do you call this?
This is called a panel switch.
So Sarah, you're the switch witch?
Yes.
You're the specialist of the system, and I understand it's fairly rare.
Yeah, based on all of the research I've done, this is the only one left in the entire world.
I'm trying to focus on the contacts themselves. They're in this huge matrix of little contacts.
Yeah, they're arranged in these large panels called banks. And in each bank, there are 100 sets of contacts all sandwiched on top of each other.
It's amazing. Can you move one of those little brushes that goes and contacts them out there on rods?
Each brush has to stop within a fraction of an inch on the contact.
They're actuated from down there?
Yeah, they're controlled by these segments down here. These are actually clutches. And if I operate a clutch, I can force the rod to go up and down. So the motors are always running, the rollers are always spinning, and when we want to move a brush, all we have to do is actuate a clutch, either up or down drive, and we can move the brush wherever we want. At the top of each of these rods on this frame,
I can't get to it.
Yeah,
that's this one.
Top bank there, yep.
Right.
These are called commutators. As the rod is traveling upwards, these springs down here are attached to the rod, and they move over these commutators. And as they do, they send pulses back to the control mechanism. It's called the sender. The sender counts the pulses, and when it's counted the correct number that it's looking for, it pulls the power and instructs the brush to stop moving.
Here there's some digital computing involved in this system.
Exactly.
So here we're going to move from our, how do you call them, the panel, to the computing part of it. Ta-da!
So in telephone parlance, this is called a sender, but it is very much an early relay computer, designed at the same time in the 1920s. And the job of this sender is to monitor and store the digits that are being dialed into it. Once it's received a certain number of digits, it performs a lookup against a shared database, which is all the way over there. That database returns values to the sender, and then it uses those values to direct the rods on the frames where they need to go to build the mechanical connection for that call.
So it's one big step ahead of the Strowger thing, right?
Yes.
It has registers, it remembers your number, it knows how many pulses it have to move, it subtracts them from the pulses it receives, so it's a little ALU in there. Amazing, let's make it work.
All right, let's do it. magic button.
Oh man, this is the mother of all panels.
So these are calls that are going through the system right now. They're actually going to progress this way. So one call takes a bunch of frames to set up.
Oh, I missed that when these started to go up. Oh, there we go. It's just alright. It's the matrix. And then during that time, the relays are. Is that one used? Yes, it is.
Yep.
It's clicking like crazy. So what's this big thing doing, Sarah?
So this is all test equipment. All of these jacks are the lines that run from one central office to another in town. They all appear as jacks here.
So those are trunks?
These are trunks, exactly.
Okay.
And if someone reports a problem that they're called in, go through, I can figure out what trunk they were using, plug into it, and then I have a voltmeter circuit here.
Oh yeah, nice one.
So I can do voltage tests, I could do resistance tests on it, and I can make sure that the electrical characteristics of the trunk are what I expect them to be. If they're not, I would just fill out a ticket and send it out for repair. The other cool thing I can do is I can place a test call on the trunk as well. So by using these keys.
Oh, you can dial something. Yeah, it looks like you should be able to control a moon landing from here.
Yeah, basically. In the original days of this switch, you'd have two people sitting here basically at all times.
Really?
Just testing and monitoring.
And making sure the honking machine behaves. The honking machine it is. So we're leaving our amazing panel to go to the next step of evolution, which would be Crossbar.
Yeah.
So Crossbar is another wonder of technology.
So this is called a number 5 crossbar. It wasn't the first crossbar, but it's a really great example of how the machine works. So on the crossbar system, you have a bunch of verticals that can each be operated. These are individual magnets here. And then you have 10 horizontal levels that you can select from. So what I'm going to do is I'm going to connect any vertical to any horizontal just by operating 2 magnets. So if I want to do that, I've just connected that cross point right there.
And it stays connected by some kind of miracle.
And as long as this vertical magnet is held, this cross point will stay connected. So the select magnet can be released, but the vertical magnet will actually hold that connection up for as long as it's operated. And what's happening here is these select magnets have little wire fingers that are sticking out of them into that crossbar switch matrix. And that wire can go either up or down, right? And when that wire goes up or down, it interferes with that vertical magnet, and when that vertical comes in to close the connection, it pushes that wire in, which then causes these contacts in here to actually close. But if you look at these contacts right here, right where my finger is, and I go horizontal, and vertical, you can see them closing in there.
Yes, we see it.
So,
and I mean the genius of that thing is that it's non-blocking.
Exactly.
Right.
Yeah.
So you can have any or all of the contacts on or off at the same time. All the positions are valid. You don't have to wait for something to be available or not. They are all available to you at all times.
Right. And the control element of this, called a marker, which I'll show you, can observe the state of the entire switching network all at once, and then make a decision about how to route that call or how to connect it. And if the first route is not available, it can try again and again and again.
And also very scalable because it's a regular left and right matrix. So it looks... Actually, they made memories out of that for relay computers at first because it's so scalable. And if you have seen my video about the Japanese Facom 129B relay computer, you will have recognized the devices they use to make their 23,000 bits of memory. Yep, this computer's RAM is made out of this very crossbar elements.
The hardest part about it is connecting up the 600 wires to, for the next thing, but if you want to make this bigger, you can basically just drop in a new frame.
So very scalable.
It's very, very scalable.
I hear the noise, but I don't see anything.
Look up here. You'll see it eventually.
Yeah. Yeah, it's also much faster than the panel, right? Because it doesn't have to travel. Well, as in the other machine, this one has also a set of test equipment, but it's even better.
It's even better. One of the ways they did that is with this trouble recorder, which actually prints out a physical record whenever this machine encounters a failure. So I can simulate that for you. All right, so look here.
Okay, I'm looking. Oh.
It's a punched card, and the holes in the card are sort of a stack trace. And then we can take these cards, and by looking at the holes in them, we can see...
Figure out what the problem is.
Yep.
Little holes, little punch card. Well, it's a little punch card, it's a big punch card.
Big punch card.
Okay, we'll have to skip over other wonders of machinery, including the calculograph cold timer clock and the automated cold billing punching machine, so we can rejoin the electronic age with the 3 ESS computerized switch, courtesy of Bell Labs.
So now we're doing a giant leap in the future. We're in 1970 something, 1976, and it has been computerized, and this is
Number 3 ESS.
3 ESS. So when I went at Bell Labs, I came to the scene when they were at the 5 ESS, and it was a big deal.
So we're just gonna apply 48 volts to everything.
Oh, 48 volts, of course. Ooh, I heard relays.
Right, all the relays lit up. And now there's a bunch of power converters on the other side that we have to turn on to get the
Okay, go for it.
voltages that this runs on. And these are various peripherals that the computer is going to want to use once it starts to come to life. And we'll turn on this computer. Need to flip a switch in the back. And we're going to turn on the other computer. So this is a redundant pair of computers. It's going to take several minutes for it to read that tape drive.
Okay,
but you can see its sort of progress indication there, just to say it is doing something.
I was asking if it was typical 1975 technologies, TTL, and the answer is yes and no. There's some stuff that looks like it would have gone on the moon, and which is chips on ceramic. Heydays of Bell Labs, right, where they could do anything they wanted. You can also see why Linux came out of Bell Labs, because they needed a computer that was A, secure, and B, would work 24 hours a day. You didn't need to reboot, right? Could recover from a fault.
Although this system's not running Unix, the software development trouble, the hassle they had with doing that was one of the big inspirations for Bell Labs to say, okay, we need to have an operating system that not only can be a real-time OS for these machines, but also a development platform for the software that's going to be running on them.
So it's truly the switch computers influence Unix.
Absolutely.
What would be the terminal that would be on there?
This guy here.
A teletype.
Oh, an ASR33?
35 is what originally.
Yeah, 35 would
and
be.
ours is in storage, and we have not made the trip out to storage to put it
35
back.
would be the much more ruggedized version of the 33.
It's up.
It's running.
Oh, that's it?
That's it.
I hear click click, it's the seconds.
Yep.
Oh yeah, and it's telling it to you very, very, very slowly at whatever bauds per
110 baud, yes,
Yeah.
exactly.
It's crying out loud for a mechanical terminal. How many of those are still around?
These machines?
Yeah,
0.
all gone.
This like our panel. We're pretty sure this is the only preserved example.
Wow.
So you don't end a line with the enter key, you end a line with bang.
Mm.
And then it just tells you right away, printout follows, which means it's working and it will eventually get back to you.
Very terse.
Very, very terse. Again, because teletype.
Teletype, right.
Yeah.
You can't be chatty on teletype.
Okay, diagnostics of the CU complete. All tests pass. That's what we really like.
You have to know your shorthand pretty good.
Yeah, you do. Aha! And now we get the system normal light.
It's working.
Got it.
That's what we like to see.
Ooh, very nice.
So now we should be in a position to make a call, so we do.
There we go.
All right. We have it. Go for it, Peter.
Hello.
Hello.
Oh yes, I think Mark is here. Let me see if I can get him for you.
Okay, thank you.
We use this small machine to make a phone call.
Yeah.
Amazing.
So next time you use a computer, take a minute to thank the telephone and Bell Labs and their invention of the transistor and Unix and its derivatives. And don't forget, if you're in Seattle on Sundays, there is a gem of a museum waiting for you to visit. See you in the next episode!